Math 2414, improper integrals. Infinite limits of integration, example 5, p integrals. Now what do I mean by a p integral? Well, a p integral is kind of a name that I just coined, and I may have heard it somewhere and it might actually be a legit thing. But the reason I'm coining this phrase, assuming that I did, is when we get to the sections about infinite series and sequences, there's something called a p-series, which is a thing, and it's intimately related to integrals of this type, hence I'm going to call them p integrals. But what do I mean by that? A p integral, it's a little bit better, is an integral of the form integral from 1 to infinity of 1 over x to the p dx. And we're going to answer the question for what values of p does the integral converge, and for what values does it diverge. And by the way, the p stands for power. Now we've actually seen a couple of p integrals already. The very first one we did was the integral from 1 to infinity of 1 over x squared dx, which is a p integral with a power equal to 2. That converged to 1. And in the next example, we did the integral from 1 to infinity of 1 over x dx, and that diverges. And that's a p integral with p equal to 1. So we've already found one example of convergence and one example of divergence. Our goal here is to completely categorize when will this converge based on the power, when will it diverge based on the power. So how do you attack something like this? The answer is you start out generic and then you prepare to do some analysis. So what do I mean by start out generic? Well, what would our first move be? Our first move would be to replace the infinity with a t and then try to execute this integral, try to do this integral. Normally when you integrate, I don't know why I got that word stuck in my head. Normally when you integrate the reciprocal of a power, you rewrite it as a negative power. So we're going to integrate x to the negative p power. And how would you do that? Well, how you do it actually depends upon what the power is. Most of the time, you take the power, add 1 to it, so we get negative p plus 1, and then multiply by the reciprocal of that, so 1 over negative p plus 1, and then you evaluate it from 1 to t. But there's one time when you wouldn't do that, because there's one power that would create a problem here. What power for p would make this denominator 0? If p were 1, then negative p would be negative 1, and negative 1 plus 1 is 0, and that's bad because it's in a denominator. So this is what would happen if the p was not 1. Because if the p were 1, it would be undefined. So what do we do if p is 1? Well, if p is 1, then this is x to the negative 1 power. But x to the negative 1 power means 1 over x, and when we integrate 1 over x, we get the natural log. So it would be the natural log of x from 1 to t if p is equal to 1. So we've got to be very careful not to just assume things, especially when unknown denominators make their way into the picture, that you can't let it be 0. So this is how we would evaluate this integral depending upon whether or not the p is equal to 1. But remember, our goal is to figure out when does this integral converge and when does it diverge. And we already know what happens when p equals 1. When p equals 1, we get a divergent p integral. So we really don't need to worry about the case p equals 1. So let's go back to the very beginning and stipulate that the power is not equal to 1. We've already figured that case out. And if the power is not equal to 1, then we don't have to worry about this, which means I really don't have to consider two cases here. Excuse me. We can just continue evaluating this. Let me write it a little bit better. 1 over negative p plus 1 times x to the negative p plus 1. And we're evaluating this from 1 to t. Now be careful. These limits of integration represent values for x, so the x will be replaced with a t, and the x will be replaced with a 1. The p is just an unknown constant. If I substitute t, I get 1 over negative p. You know what? Let's do something here. There's nothing wrong with negative p plus 1. But addition is commutative, so I can reverse the order of that and write it as 1 plus negative p. But 1 plus negative p is just 1 minus p. I think it'll look better as 1 minus p instead of negative p plus 1. All right, so we have 1 over 1 minus p times t to the 1 minus p. Remember, we're substituting the upper limit. Minus, if we substitute 1 for the x, we get 1 over 1 minus p times 1 to the 1 minus p, but this is just equal to 1. So 1 times 1 over 1 minus p is 1 over 1 minus p. So our definite integral becomes 1 over 1 minus p times t to the 1 minus p minus 1 over 1 minus p. All right, so we got the first part of the task done. We figured out what this integral looks like in general when we don't know exactly what that power is. And again, if the power were 1, we would be in trouble, but we already excluded that because we know the result there. So what's our second move? Well, our second move is to take the limit as t approaches the infinity. T approaches infinity of the antiderivative. 1 over 1 minus p times t to the 1 minus p power minus 1 over 1 minus p. Okay, well, let's think about this. This is a limit as t does something. Relative to t, the p is just sitting still, it's constant. So everything that's just p's doesn't change. This stays the same, this stays the same. But the t to the 1 minus p, that's where we have to focus. So let's focus on that for a second. In other words, what I'm saying is we can move the limit right there. We can move the limit inside to just the part that has the t. And if you really want a justification, it has to do with continuity, but let's not dwell on that too much. I'm only writing the limit where it's going to happen on the t to the 1 minus p. So let's focus on this for a second. We've got t raised to a power, and the t is going to get infinitely large. What's going to happen? Well, it depends on whether the power is positive or negative. If this power is positive, if 1 minus p is greater than 0, then the limit as t approaches infinity of t to the 1 minus p, we have infinity raised to a positive power, which is infinitely large. In other words, it diverges. And just like that, we've got a categorization of when this thing definitely diverges. It diverges if 1 minus p is greater than 0. But if we add p to both sides, that means 1 is greater than p, which is the same as saying that p is less than 1. Now we know when this thing diverges, or at least we know what happens when p is less than 1. We know the integral from 1 to infinity of 1 over x to the p dx diverges if p is less than 1. And the reason is actually pretty easy to explain. If this power is less than 1, then when we move it upstairs, it becomes greater than -1. Let that sink in. And when we integrate it, we add 1 to it. If you take a number greater than -1 and add 1 to it, it will become greater than 0, aka positive. So when this power down here is less than 1, integrating it puts it upstairs as a positive power, and the infinity on top makes the whole thing blow up. But that's what happens if the power here is positive. But let's see what happens if that power is negative. If this power is negative, then p minus 1 is positive. Let that sink in. If you have a negative number for a subtraction problem, reverse the subtraction problem, it comes out positive. So the limit as t approaches infinity of t to the 1 minus p is equal to the limit as t approaches infinity of 1 over t to the p minus 1. And again, let that sink in for a second. All I did is reciprocate it to the denominator, which negated its exponent, but the negative of 1 minus p is p minus 1. And right now, p minus 1 is positive, so we get 1 over a positive power of infinity which converges to 0, static numerator, ever-growing denominator, fraction collapses. So if this power here is negative, then I can do this limit. So we'll just say the limit equals, this goes to 0. So we have 1 over 1 minus p times 0 minus 1 over 1 minus p. We're right here. But 0 kills that, and we get negative 1 over 1 minus p. But if we slide the negative to the denominator, distribute it, and turn the problem around, we get 1 over p minus 1. Well, that's a pretty big claim. Oh wait, but for what values of p does this happen? Well, if this is true, or if that's true, but if we add 1 to both sides, that means p is greater than 1. So, the integral from 1 to infinity of 1 over x to the p dx is equal to that limit, 1 over p minus 1, if p is greater than 1. Now, you don't have to remember this outcome. You can just integrate it whenever you have a specific power here. We're just talking generalities here. So now we know everything about this integral. We know when it converges, we know when it diverges. It converges for powers greater than 1, and it diverges whenever the power is 1 or less. So if we wanted to summarize this, and again, we're being there's no kind of to it, we're being theoretical here. In reality, if you had a specific power here, you would probably just do the integral. But it's nice to be able to tackle things from a generic perspective and see how theoretical you can handle, how much theory you can handle. So, here's what we know. The integral from 1 to infinity of 1 over x to the p dx diverges if p is less than 1 or if p is equal to 1. So we can say if p is less than or equal to 1. And it converges, but not only converges, it converges to 1 over p minus 1 if p is greater than 1. And we've completely categorized everything that this integral can do. If you are okay up to here, you're going to be fine. This was just me pushing the envelope a little bit. But again, when we get to this section about infinite series, we will visit p series, which is going to ring very familiar with this.